Our next talk stays in Europe and explores the production and transport segments of the hydrogen value chain as analyzed in a new study on imported fuels for long-distance trucking here in Germany. Zerhusen is Senior Consultant for Energy and Hydrogen Topics at the Ludwig Bölkow Systemtechnik. And ladies and gentlemen, let me just remind you that you are very welcome to submit questions for all of the speakers in the rest of the workshop. Please send them to us via the Q&A tab on our live stream. And Zerhusen, you have the floor.
Thank you, Melinda, once again for the introduction. Hello, everybody, and this time, good afternoon. Also here from my side, from our office in Munich. It's a pleasure for me to talk to you about imported hydrogen fuels for long-distance trucking in Germany. And when I say hydrogen fuels in my presentation, I not only mean 70 megapascal gaseous fuel as it's already commercially available, for example, for light-duty vehicles and buses. No, I also then mean liquid hydrogen fuel and cryo-compressed fuels. And the abbreviations I will use are LH2 for that and CCH2 for the cryo-compressed hydrogen. Now, if you're not familiar with the German National Hydrogen Strategy, you might wonder why the title of this presentation actually says imported hydrogen fuels. Well, there are actually two very important aspects in the German National Strategy when we talk about hydrogen fuels today. The German National Strategy, which was published last year, first of all, has a very strong focus on green hydrogen, meaning hydrogen based on renewable electricity. So that's very important to understand. And secondly, the German strategy has a strong focus on hydrogen imports. And that's just due to the fact that it is expected that there will not be sufficient renewable potentials in Germany to produce all the green hydrogen we need. So as a consequence, we need to import rather large amounts of hydrogen in the future. Not only from countries within the European Union, but most likely also from countries outside the European Union. Having this, we can go to the next slide to have a look at the content of my presentation today. So what topics will I talk about? Well, first of all, I will introduce a possible ramp-up scenario for fuel cell trucks in Germany for the 2 years 2030 and 2035. I will then present the main elements of an import-based hydrogen fuel supply chain, and we will also have a look at the resulting hydrogen fuel costs. And when we discuss hydrogen fuel costs, we will also take a more deeper look into the distribution part of those costs and how we can minimize them. Afterwards, there is another very important aspect about the hydrogen fuels we will cover, and that's the related greenhouse gas emissions. At the end, we will wrap things up with some key messages, which I picked up all the way throughout the presentation today. We can move to the next slide, please. Before I go into details, I would like to give a brief overall overview to the context in which those numbers and this study actually was produced. Last year, the Daimler Truck AG presented their current fuel cell truck activities, and those include the development of technical foundations for a 40 metric ton long-distance fuel cell truck, and that also includes the certification and the real-world testing of 2 vehicle prototypes. Now, there are a very large number of fuel cell truck activities currently worldwide, also in Europe and in Germany. But there's at least one very important difference between the activities from Daimler and most of the other truck fuel cell activities right now. Daimler in those prototypes will use liquid hydrogen onboard storage to propel their truck. And that's, I think, maybe not the only project worldwide, but one of very few ones. Now, as part of their in-house activities, development activities, Daimler contracted a study, and that study should take a look at a possible a ramp-up scenario for fuel cell trucks in Germany. And that study should also take a close look on the possible fuel supply chain from production all the way to the nozzle, to the dispenser, and here analyze the resulting costs and greenhouse gas emission. And now that's when we come into play, our consortium. That contract went to a consortium of 3 companies. One of them being the company Prognos, and that company took responsibility for the vehicle rollout scenario and also for the calculation of the overall fuel demand in Germany for those trucks. Then the company I work for, Ludwig Bölker Systemtechnik, we were in charge of the supply chain analysis with a focus on the economics. And last but not least, the third company was Sphera, or is Sphera, which had the overall coordination of the consortium and which took responsibility of the environmental analysis. And that's the main context in which the study was produced. And I'm glad that I can present some of the results today in this workshop. Next slide, please. Now, before we look onto the detailed numbers of those vehicles, we need to talk about the main drivers in Europe, why fuel cell trucks will come on the roads in the next few years. As you might know, in Europe, we have different greenhouse gas emission targets for the road vehicle sector. There has been one for light-duty vehicle for quite a few years now. And then in the last year, or last 2 years, there's now also been a target for heavy-duty vehicles, and that target says you have to achieve a emission reduction of minus 30% by 2030 over the base year, and in this case, the base year is 2019, and the 30% reduction relates to new vehicle sales, so new truck sales. That's important to understand. For our scenario development, we also needed some target for 2035. However, for 2035, there's not an official target yet. So we defined a greenhouse gas emission reduction of new sold vehicles of at least 50% to develop our scenario. Then further, we assumed that within the European Union, Germany will be one of the few countries who will overachieve the goals by 2030 and 2035. And that's just to compensate for other countries which might have fewer vehicle sales in that time. As mentioned before, the target is an average target over the entire European Union, so you can overachieve in one country and underachieve in another country, and that's allowed. In our scenario, of course, we also analyzed the impact of the battery truck deployment. However, we assumed that battery trucks will mainly be used for driving applications with a daily driving distance below 400 kilometers, and also for applications which do not have space and weight restrictions. So the European goal is not only achieved with fuel cell trucks, but with a mixture of fuel cell trucks and battery trucks, and in fact also with some improvement in the internal combustion engines of the conventional vehicles. So we have an overall scenario, and now we will only have a look at the fuel cell part of that scenario. Now, what fuel cell trucks did we consider in our analysis? Well, we had a strong focus on trucks in which fuel cells make sense. So that's the heavy duty and long haul trucks. And in Europe, we call those the Vecto classes 5 and 9. And Vecto classes, that's a European terminology which is also used for the emission calculation. You can look that up in the internet if you wish to. But those two classes are actually the most relevant classes within the European Union, and they account for a very high share of the overall trucking emission, and that's due to their high specific consumption due to the weight, and also to the high annual driving mileage of those vehicle classes. Now, if we look on the left graphic, you see the development of the vehicle stock of those fuel cell trucks in Germany. There will only be a few hundred trucks at first, prototypes and small demonstration projects most likely. But then in 2030, we will already have 37,000 trucks on the road in Germany, fuel cell trucks. And that will ramp up quite quickly to 180,000 trucks by 2035. Now, there are two very important reasons for this rather quick and steep ramp up of the vehicle numbers. The one reason is again related to greenhouse gas emissions. As the United States and other countries, Europe wants to be net zero greenhouse gas emitting by 2050. So if we want to have a 100% emission-free fleet on the road by that time, we need to start selling emission-free vehicles only about 1 decade ahead to be able to replace all the old vehicles. And that means that by 2040, yes, we have to bring the diesel with fossil diesel fuel out of our streets. And the second reason for this quick ramp up is actually the fact that vehicle manufacturers will most likely not be interested in producing multiple propulsion systems in parallel. So during that period, they might have to produce fuel cell trucks, battery trucks, diesel trucks, maybe even natural gas trucks, and to reduce the period in which they have to produce those 4 different propulsion systems, that's a very important aspect also for those manufacturers. On the right-hand side, you see a graphic of an intermediate result we produced in the project, and that's the German highway system for 2030 and 2035. And the colors indicate the number of fuel cell trucks per day you would expect on certain sections of this highway system. The darker the color, the more trucks you expect in that area. Those numbers were used in our study to estimate the quantity and the size of the refueling stations, for example, but also to calculate the overall fuel demand. And that's what we will have a look at on the next slide, please. Now, based on this fuel cell truck rollout scenario, the calculated fuel demand just for those vehicle classes we consider is 0.3 megatons of hydrogen in 2030, and that quite quickly fivefolds to 1.5 megatons by 2035. Now, it's quite difficult to imagine how much 1.5 megatons of hydrogen are. So I've put down here some numbers to give a good impression of that large quantity of hydrogen fuel. You could produce 1.5 megatons with 20 gigawatts of electrolysis at about 50% utilization. However, you could also import that with a large hydrogen pipeline with a capacity of about 10 gigawatts, or by importing liquid hydrogen with a liquid hydrogen carrier, for example, from North Africa to Germany, and you would then need 6 carriers. And that does not mean you need 6 loads of hydrogen. No, you need 6 carriers going permanently back and forth between North Africa and Germany to import that amount of green hydrogen. Otherwise, you could also use 1.4 million truckloads of compressed gas, but however, that's quite not feasible. Now, if we move to the right-hand side, we see the number for the infrastructure. For this fuel amount, we could use about 750 refueling stations with 8 tons per day each. And out of those stations, about 350 would be located at the highway system. And for comparison's sake, that's roundabout very roughly the same amount of refueling station we currently have on the highway system in Germany. So it would enable a quite extensive network already. 1.5 megatons would also save 5.6 billion liters of diesel and save 15 megatons of CO2, and in addition, a large quantity of other emissions such as NOx and yes. Currently, the overall fuel demand in Germany for industry and all applications is about 1.6 megatons. So we are very close in doubling this demand just with the fuel we need. And based on the national strategy, there is a projection for 2030 where it says, okay, around about 3 megatons of hydrogen will be needed in Germany. So by 2030, just about 10% of the overall demand could come from this road vehicle sector. Now, on the next slide, you see an overview of the hydrogen fuel supply chains we considered in our study. As mentioned before, Germany has a strong focus on green hydrogen imports, and there are a lot of discussions about importing hydrogen from Australia or from Chile or other countries. So we have considered here quite a large number of countries and supply chains, because for some countries we did not only look at pipeline, but also on LH2 imports or even liquid organic hydrogen carriers. For today's presentation, I had to pick an example we can look at, because that's just too much to bring into this half hour. So our example for today will be the hydrogen export from Morocco to Germany. And we will look at two cases. The one case will be the pipeline import case via Spain and France to Germany. And the other option will be the liquid hydrogen import via shipping to northern Germany. On the next slide, we will start by looking at the most relevant supply chain elements that would be required to enable such a supply chain for hydrogen fuels. On the left part of this slide, you have the facilities that need to be located at the export country. And on the right-hand side, you have the facilities located at the import country. We have shown in this graph both export-import options. On the top, you see the option with the export and import via LH2 shipping. And on the bottom, you see the pipeline case. Now, when we look at the supply chain in detail here, we can start on the very left-hand side with the hydrogen production. For our analysis, we have defined a photovoltaic-based, electrolysis-based hydrogen production, and the produced hydrogen is fed to a liquefaction plant, at least one part of this hydrogen stream. The other part of the hydrogen stream is fed to a local storage for hydrogen. And that enables us to operate the liquefier at a rather constant level. As you might know, processes like liquefaction are not very dynamically, so you cannot change loads too quickly, and you don't want to turn it on and turn it off frequently. So you need some hydrogen buffer in between to enable a more or less 24/7 operation of such a plant. Now then, of course, you would also need electricity to power that plant during the night and morning and evening periods. And to enable this, we have foreseen in our analysis a plant based on concentrated solar power. And that plant has a large solar or thermal storage, and that enables electricity production from that thermal storage also during nighttime periods to power the process. Now, after the liquefaction, the hydrogen is stored and then exported via ship to Germany, where it's stationary stored again for a short period of time before being trucked to the refueling stations. And then, depending on what hydrogen fuel you want to consider, you need, of course, different types of refueling stations. For the case of LH2 hydrogen fuel, you need a more or less a rather simple hydrogen transfer pump from your local refueling station storage to the truck. If you want to use cryocompressed hydrogen fuel, you need a cryo pump for this hydrogen transfer. And if you want to dispense 70 megapascal, you need a cryo pump and a evaporator to produce high pressure hydrogen gas. Now, that's one option. The second option is hydrogen export via pipeline. Here, we don't need an extra storage. We have assumed that you can dimension this export pipeline, that it is astoric intrinsically to outbalance the fluctuating hydrogen production. And then once the pipeline is in Germany, you have two options, and which one you choose depends on the fuel you want to have at the end. You can either feed from this pipeline to a liquefaction plant, and now in this case, the liquefaction plant would be powered by electricity from the German grid. And then again, you have the distribution to the different refueling stations. The second option here is to feed from the pipeline to a trailer filling facilities for gases, road transport, for example, at 50 megapascal, which we have considered in our study, to transport the hydrogen to the refueling station for 70 megapascal. Now, on the next slide, we see on the figure, we see the overall resulting hydrogen fuel costs, and that's costs considering well to nozzle, so everything is included up until the nozzle of the refueling station. And you see on the left two stacked bars, that's for the LH2 shipping and the different fuels, and the right two bars are for the pipeline case. And in this graphic, and also in all the other graphics following on the slides, we have combined LH2 fuel and CCH2 fuel into one stacked bar. And that's just due to the fact that after our analysis, we have seen that the cost and the emission differences between the LH2 and the CCH2 fuel are really minor. There might be a slight cost premium for the CCH2. Also in terms of emission, but it's really minor, and it does not make sense in such a graphic to point that out. So to make it more simple, we have combined those two fuels. And if you look at the numbers here in this graphic, you can see quite easily that fuel costs of 4 to 5 euro per kilogram are feasible for 70 megapascal fuel, but also for LH2 and CCH2 hydrogen fuels. However, there is a certain cost advantage here in this graphic for LH2 and CCH2 fuel, and that's indicated by those black downwards arrows. If you compare those stacked bars and the colors of those bars, you see this difference mainly comes from the light and dark green, and that's for the road distribution and the refueling station. And as you have seen on the slide before, we have assumed distribution with a truck. And now on the very right-hand side, you see actually the impact of the trucking distance on the overall fuel costs. For our base case analysis, we have assumed the average road transport distance of the fuel. And now on the right-hand graph, you see this error indication, and this does not indicate an error, but a bandwidth of minimum and maximum distribution. So if you have a average transport distribution distance, of course, you also have always refueling stations that are a lot shorter to drive and a lot longer to drive to supply with hydrogen fuel. And here you see this very large impact. Now you might ask, okay, why did you choose trucking as distribution option? Isn't this rather expensive and increases the costs of the hydrogen fuel? And then I would say, yes, that's true. And that's why we look at the next slide. Here we have done a sensitivity analysis, and we have reduced the trucking distance from the import location to the refueling station by adding a national pipeline system. Now, on the left-hand side, you see the assumptions for the base case. For the example of pipeline import from Morocco, you see on the bottom left, there's this green arrow, and this is a pipeline that goes to a industrial center in Germany. And from this point, you have this national distribution by truck. And here we have indicated the average transport distances, which from this location to all the refueling stations in Germany would be around about 325 kilometers. And now if we move to the right-hand side, to the right-hand graphic, you see those lines. That's the national distribution system by pipeline. And then you have those little red triangles. And those triangles, they indicate now regional hydrogen outlets. And each of those triangles could be a regional liquefier or a trailer facility for gaseous hydrogen road transport. And then, of course, that reduces the transport distance. And we have done the analysis. If we would assume this hydrogen backbone here, this green one, and that's not our idea to build it like this, that's actually a concept proposed by the European gas transport system operators last year and updated this year, and we've just taken their idea and put it in the graphic and added those liquefiers. However, that reduces the transport distance from 325 kilometers to 75 kilometers in that case. And that significantly reduces the transport costs, as large-scale pipeline transport is, of course, a lot more cost-efficient than road trailer transport by with liquids or gaseous hydrogen. And that's now only one example how you could reduce this last-mile road delivery. You could also apply different means of distribution. For example, you could use inland shipping of liquid hydrogen from the coast. You see on the left graphic, in Germany, we only have coast in the northern part. So that's where all the ships come in. And from that, you have to go all the way down to the south. But we have some rivers, for example, the Rhine, and you could take the hydrogen onto a river barge and bring it up the river, or you could use the railway system for cost-efficient transport. Now, on the next slide, we see actually the impact of this pipeline system, of this sensitivity analysis. The graphic on the left-hand side, that's still the same than 2 slides ago. But now on the right-hand side, you see those stacked bars, and that's the result for the supply case with this national hydrogen backbone. And you can see that those 2 bars are reduced, and that's indicated by this black arrow. And you see, first of all, that you have a rather big decrease for the 70 megapascal fuel, and that's just due to the fact that here we have assumed gaseous hydrogen transport by trailer with 50 megapascal, and that's rather expensive compared to liquid hydrogen transport, which is the other stacked bar. And here you only have a, let's say, rather marginal cost reduction. But at the end, what happens is that the cost gap between those 3 fuels is significantly reduced. In this graphic, you can still see there is some cost advantage of LH2 and CCH2 over 70 megapascal. However, you see they get really close. And then you could also do the analysis for other distribution options. But you see how important the choice of the last mile distribution option is if you consider the overall import supply chain from hydrogen production in another country, transport to Germany, distribution in Germany, and then refueling station and refueling. The distribution option is really relevant for the overall fuel costs. And by applying a pipeline system, you can reduce those costs compared to the trailer solution. Now, having talked about the resulting fuel costs, we can have a look at the greenhouse gas emissions on the next slide, please. First of all, on this slide, I would like to mention that the greenhouse gas emissions shown on include all emissions from the production to the nozzle and all CAPEX emissions as well. CAPEX emissions, some know that as gray emissions. Those are the emissions that are related with the production of the equipment. So to say the production of the photovoltaic module, the production of the pipeline or the refueling station. So that's all included in those figures. And we see, first of all, the 2 bars on the left, they are more or less equal. So again, LH2 and CCH2 and 70 megapascal show the same carbon footprint. There is a marginal difference again for 70 megapascal, but you can barely see it in the graphic. So it's more or less the same here. And then for the pipeline import case, you see there is some difference, and it's quite obvious where this difference comes from, and that's this orange yellowish section, and that's the liquefaction in Germany. And you remember, I've already mentioned that in this case, where we import hydrogen via pipeline, we have the liquefaction in Germany, and that's powered by grid electricity. And in 2035 in Germany, we still have gas-powered plants on the grid, and also still some coal-powered plants. The coal phase-out is a few years later. So that quite heavily impacts on the footprint of this fuel in this case. That's just due to the electricity consumption of the liquefier. For the 70 megapascal option, you see a little dark green section and a little bigger light green section, and that's just the electricity, again, also from the German grid mix to power the compressor for filling the transport trailer at first, and then also for further compression at the refueling station. On the right-hand side, you see, just for comparison's sake, what could be achieved if you would place a electrolyzer right next to a refueling station in Germany, and then your carbon footprint depends significantly on the choice of electricity you use. If you use grid electricity, it's very high bar, and if you would use, for example, just wind power, you can reduce the overall emissions of your fuel. But if you compare the national on-site production and the import supply chain, you understand that there is not too much of a difference between those fuels. They are all can be considered low carbon fuel supply chains, and that's quite important to understand that the import of hydrogen does not necessarily mean that you have higher greenhouse gas emissions related with that. We also found out by analyzing the data that the infrastructure for hydrogen actually only has a marginal impact on the overall emissions here. So the production of the electrolyzer or the refueling station itself, is not that important. It's usually the operation of the refueling station or the compressor or the liquefier and the greenhouse gas emission that are related to the production of the photovoltaic modules, which are used to power the electrolyzer. That's the big blue part on the bottom. So those are the important aspects. Now, let's wrap things up on the last slide, please. Let's have a look at the key messages. Number one, 2035, 1.5 megatons of hydrogen fuel demand just for those two truck classes we considered. And this demand already justifies a nationwide comprehensive refueling network. So no matter what other vehicle classes would do, battery, other forms of hydrogen fuel, just for the long-haul heavy-duty trucks, it would be quite feasible to establish a refueling station network in Germany. And number two, it could be around about 700 refueling stations, 750, of which 350 are located at the highway system. And then more importantly, number three, here by 2035, we can assure that it's possible to achieve fuel costs of below €5 per kilograms for all three hydrogen fuels. And here I have to mention that our assumptions regarding hydrogen production technologies, that means the electrolyzer and also the renewable electricity, those assumptions are rather conservative in our study. So if you would look at more recent cost projections for electrolysis and renewables, you could also here be more aggressive in terms of cost reduction, and then we could also see even lower fuel costs in Germany from imported hydrogen fuels. Or if you would switch to blue hydrogen, that might also enable further cost reductions, at least in the medium term. Number four is also very important, and that's about the compatibility of imports and fuels. What we have seen is that if you import liquid hydrogen, of course, it's quite feasible to also dispense liquid hydrogen, but it's also feasible to use liquid hydrogen imports to dispense gaseous hydrogen. And that's something which some of you might already know. That's not too new, but also the other way around is quite feasible. You can have pipeline imports and then have national liquefaction, and then use this liquefied hydrogen for LH2 fuel or cryocompressed fuel. And that's something that's really interesting to understand, that no matter your choice of hydrogen import, you're always free to choose the fuel whatever you want. So we do not have any limits here. Number 5, we have seen that a national distribution infrastructure is required, an efficient one, to ensure low hydrogen fuel costs, and that could be a national backbone, or as mentioned, inland shipping or rail transport. And with number 6, we have seen that for all the fuel types, we can achieve quite low greenhouse gas emissions, even though if we import the hydrogen. Now, that was my presentation. Thank you very much for your attention. In case you have any questions, we will have a Q&A session right now. And if you come up with additional questions later on, please feel free to contact me or any of my colleagues from this project consortium. Thank you very much.